so now we have Jacobo Asorey, who's going to tell us about updating cosmological tensions using the most recent datasets from early and late universe groups. Thanks so much.
Thank you so much. I want to start thanking the organizers for giving me the spot to show this recent work I've been doing with a collaborator at Complutense, Universidad Complutense de Madrid, Javier de Cruz Pérez, who I think gave a talk on the previous CosmoVerse conference on a different topic. So I basically, the title is not the best title ever, but I literally will be speaking about some check we've been doing on the tensions using the kind of newest Planck reanalysis and the latest BAO and supernovae datasets. I will start just by mentioning that in the last 100 of years of cosmological observations, we have reached a significant number of different probes. Obviously, those are not even all of them. Just in the next plot I will show, just for H0, we have way too many, or not even way too many, but way more than the ones I'm showing here. But yeah, we can predict basically the description of perturbations from homogeneity through CMB with large-scale structure, not just with BAO, but just looking at, for example, the 3 times 2PT. In this case, I showed DES, but you also have KITS and other newer surveys. This is like the latest probe in this regard, and then the other probes that are more linked to dark matter. And then obviously we have whatever we use to measure distances or H0, supernovae, gravitational waves, quasars, etc. But as this conference is about the tensions, we have this, as was shown also in the previous talk, we have this bunch of different measurements, mostly from different local measurements of the H0, of the Hubble constant, and then the early universe ones, either using CMB anisotropies or using nucleosynthesis, primordial nucleosynthesis estimates. Then I will mention another one too, but also we may have tensions regarding the amplitude of the perturbations of matter, depending if we also use CMB measurements or we use large-scale structure, mostly through lensing. I will not focus mostly on any of those in my talk, but they are related to the results that we're showing. Also, those two things can also be related with omega matter, so we can also be talking about the tension of how to measure omega matter somehow. Obviously, I know those are not the most updated checks on systematics, but things haven't changed so much. But we still haven't found whatever it may be producing these tensions from the systematics point of view, both in H0 or in sigma 8 measurements. Also, sigma 8 measurements, depending on what you look at, seem to be getting slower with the newer measurements with more data, while the H0 is kind of doing the opposite. But yeah, simple extensions, also simple theoretical extensions, sometimes alleviate it, but depending on who you talk to, but doesn't solve fully the tensions. Then now, after these many years working, people working on H0 tension, sigma 8, suddenly after the DESI results, the dark energy is again back in the room as another kind of tension thing with respect to lambda CDM, as the time-dependent dark energy kind of prefer model by the DESI combination with supernovae and BAO, because as was mentioned before, some of these results are mostly like for example, the W being a bit lower than, for a constant equation of state, being lower than -1, it's, or being higher than -1. No. Yeah, it's driven by the supernovae. Also, some of these time-dependent dark energy is also driven because in this case, the BAO is not constraining that much, so supernovae are also driving this a bit to the time-varying dark energy. So, just a summary of these anomalies, I mentioned already the H0 tension, I mentioned the sigma 8 tension, and then there is also the lensing anomaly, in which I will be focusing more in the results we got. which at least for the Planck 2018 dataset, there is the fact that there is a mismatch between the observed lensing on the power spectrum and the expected one for lambda CDM. And one way to alleviate this could be the universe has a closed curvature, although this will be obviously in tension with inflationary models or anything else, but that's another problem for this. This is also related with omega matter, as lensing depends on this, and curvature is also obviously degenerated with the curvature and the matter solution. Just this slide is not related at all, but I usually I started working on the tensions recently with Javier, and I usually work on radio cosmology. Just an advertisement on radio cosmology that obviously observing the optical, we will be sampling higher redshifts. Obviously, some of these quantities like dark energy, equation of state at higher redshifts is not that relevant, as we will see for CMB. But the thing with radio is we will be able to reach super higher redshifts. And for example, there are things that are related to all this stuff, like the regionization time, or when the universe is half regionized, the hydrogen is regionized, that is related to all these parameters. So that would be a way to try to break things on the smaller scale clustering, on the smaller scale part of the spectrum, and maybe solving some of these things. So in the future, we will have, in the next 10 years, we will be reaching these higher redshifts, even with optical surveys like Euclid or DESI already reaching redshift 3 with quasars. But then that will be really important also for discriminating models, or maybe even doing cross correlations, as these original probes I saw in the first slide have different systematics. So it would be great if we can discriminate them. Even for supernovae, we can get better measurements of the peculiar velocities, or even the lensing, how lensing affects the high redshift supernovae in terms of statistics. So, going to the main part of my talk, in 2020, array analysis with a new, basically unified pipeline for the high frequency and low frequency instruments, and also doing other stuff for Planck data, was released as MPipe and named as PR4 release. So this will be like the latest data set. And basically, to sum up, it has lower noise and lower level of systematics than the previous 2018 products, data products. And then there are at least that I'm aware of, there are two different livelihoods for this new 2020 data release. There is the CanSpect, released in 2022. And then I call it, so the PELIC is the 2018, but then this Tristam et al. Livelihood is kind of an updated PELIC, but you should not call it PELIC or whatever. But anyway, there is this recent, super recent livelihood release for the same data sets, which basically, one of the main differences is in the one from 2022, polarization data at low Ls is coming still from 2018, and mostly the new features mostly focus on the high L end, while for the Tristam et al. One, for the polarization at the low L, there is also the new livelihood, which is the lollipop, and hilipop will be the high L spectra information. And then, as you can see here, for example, for the lensing anomaly, if for 2018 we were several sigmas away from what you expect if everything is according to lambda CDM and AL is 1, these two PR4 livelihoods are closer to the lambda CDM model. And this also impacts the curvature. It's less close in that sense for any of those livelihoods when doing the cosmological parameter inference on those. Before showing the contours we got and the likelihoods we got. Basically, for count spec, which we don't use for this paper, but count spec only has this high L spectrum modified, while for this one, the low L temperature maps are still 2018, but for the polarization at low L is the lollipop likelihood from Tristan et al. And then for the high L, it's basically the TT, T, and EE maps are coming from the lollipop likelihood. Basically, in order to check these tensions, we just tried lambda CDM, obviously, but then only 4 extensions, which are basically taking into account the lensing, the A lens, which is just basically introducing this unphysical parameter when adding the lens information, and then if everything, the theory is correct, it should be 1, but then adding this as an extra parameter to lambda CDM. Then we use this is P delta of K. K is too close to 1 in the keyboard, sorry about that. But then this is basically the Planck equation for the primordial power spectrum for a non-flat universe. And then we use the WCDM model with a constant equation of state. And then finally, we try CPL as it's now again trendy. So this is just CMB data results. This is already the same thing it's in the Tristan et al. Papers. We basically agree with, that's a check in terms of well, it's not, I think they don't have the W0 and WA. I'm not showing WA because it's constrained from this, but I think they didn't do that, but for omega M, H0, and AL, and omega K, they did. Basically, we have similar omega matter measurements to the PR3, but then some measurements, I will show a comparison later, but AL is, as was shown a bit before when I was comparing, is a bit closer to 1, so is just 1 sigma-ish away. And omega K is also getting closer to 0. Then obviously we have CMB is not as great, CMB alone is not as great as trying to constrain the dark energy parameters. But then I will show what happens when we add the BAO and supernova information. And then for H0, things are similar to previous, to the PR3 measurements, so not that interesting in terms of H0 tension. Then I'm not showing it here because we decided not to show, but if we add the lensing maps also, not just in the polarization and temperature mass, but we add the lensing, the conclusions are the same, just the error bars are smaller. And also they agree with the ones that are in common, they agree with the Tristan et al. Results. It takes a bit, some of them it's taking 1 million years to converge for some of the change. Then this is the comparison with PR3. You can see how the lensing anomaly decreased with respect to the PR3, the 2018 results, and there is kind of 1.7 sigma difference between them. And then for the non-flat primordial power spectrum, also the omega K is getting closer to 0. It's just 1 sigma away from 0, more or less. So PR3 used to flavor these non-flat universes, but PR4 seems to be, or at least PR4 lollipop and lollipop likelihood seem to be favoring less PR4. Non-flat universes. And also the lensing anomaly seems to be reduced. So this is good somehow if you want to get lambda CDM, but it's also weird, not weird, but just the fact that a bit more pointings were used, that the pipeline was unified and foregrounds were removed in different ways, just changed it that much. Maybe it speaks that some work is needed in terms of checking the Planck data or choosing it. Then we basically added just the 12 DESI BAO points to the PR4, and then for the supernovae we used the Pantheon plus sample, but we didn't use any supernovae for the lower redshift, so it's just for dark energy purposes. So we cut at 0.01, so we don't have the 1700 supernovae, we have 1500 something. And then, as you can see, basically, now as usually, curvature is changed by the BAO and the supernovae went from close to open, but still is 1 sigma away from flat, or less than 1 sigma, or 1 sigma-ish. The lens is still is 1 sigma away from lambda CDM, so it's still not that tension as with PR3. And then for W, the same thing happens. The supernovae are driving W a bit different from -1. And then also we get some time-dependent dark energy equation of state. And then H naught is still having the same tension, so not solving that. And the main take from this is still, so the PR4 is the one still diminishing the tensions for the lensing anomaly and the curvature, while the other data sets are giving us the dark energy difference with lambda CDM, let's say it this way. And yeah, we're finishing the paper. We submitted it hopefully this month, if not first week of August, hopefully. And then here you have the contours, so you can see the difference between just the CMB. This is for the lambda CDM plus a lens. The difference between just when you use only the non-CMB data, obviously you are not constrained that well, but when you get the PR4, then as you can see, one it will be here, so it's within the sigma that the A lens is within the 1 sigma tension with respect to lambda CDM. And then for H naught and omega matter, things doesn't change so much between the data sets. Then this is for the curvature case. And here similar, we have something for PR4, which is consistent with flat. And then this is including the combination of all data sets, which is almost making it completely flat. And then for omega matter H naught, we have similar results. And then this is just to show that, as it should be, because we are using the DESI data, the 12 DESI BAO data points. And in this case, we only use the Pantheon plus sample. We didn't use Union 3 or DS, first 3 years of, full 5 years of supernovae taken. The first 3 years were spectroscopic, spectroscopically classified. The last 5 years, as was mentioned in the previous talk, were classified photometrically. We only use Pantheon plus, and we get something, I'm not comparing it, but just by looking at this in here, is super similar to the one I show in the third or fourth slide. But there, we get similar results to the DESI, this time varying dark energy, or if we just have an equation of a state, a constant equation of a state, but that can have a different value than -1, we get something getting a bit away from -1, so something to -0.9, mostly driven by the supernovae. So just to conclude, we still have these tensions, but just using the newest data set, so the PR4 latest livelihoods, so the Planck latest livelihoods, seem to alleviate some of these tensions, especially the curvature and the lensing anomaly. Meanwhile, adding the non-CMB data, like DESI BAO and the supernovae, in this case Pantheon plus, seem to be adding this tension on the basically dark energy with respect to lambda CDM, or cosmological constant, if you want, tension with the cosmological constant. And yeah, it will be good to do further checks, and yeah, we will we'll be checking also what happens with lensing, etc. That's for this paper, and then there are other data sets that we can be checking, but yeah, main message, these PR4 livelihoods seem to be alleviating these tensions. So yeah, thank you for your attention.
Question? Yeah. Okay. Going. So bad.
Hey, thanks. So another interesting development post DESI is on neutrino mass, and and there's this paper by Craig et al. No news is good news, where they're extending basically phenomenologically, you're saying to the negative neutrino mass, and producing a confusing picture there. And I'm wondering if anyway, just revisiting things, you've looked at all at that, and whether PR4 from they're using PR3, and I'm wondering if there's any influence of the switch to PR4 on the neutrino mass inference.
So we still haven't. So we have planned to run the chain. We still haven't done it, but yeah, we will do it. For the DESI, I think they use for the main results they show. They also check PR4. They say in the test they say but at the end for the main results they show is PR3. So 2018.
Right, they claim it doesn't make a difference. I'm just wondering if you...
For the main things they check, so the W, as I show, is basically being driven by supernovae and DESI. But they were not focusing so much on that.
Okay, thank you.
Thank you for the talk. I have a question regarding your table of the new best fit parameters. So basically you have base model and then you have to consider 3 or 4 extensions. Is there any reason why you treat all these extensions mutually exclusively? I mean, there are in principle different physics that could be behind every extension, so they are not alternative extensions, they're just extension on top of extension. So what would you get if you would consider 2 pairs and triplets of the extension at the same time?
Yeah, so the reason is time. So even just AL and omega k took some months to get convergence. The others we didn't try because we just want to show this thing. I agree some of these AL and omega k are completely degenerated. So we're interested, but yeah, we...
Do you have plans to run this Markov chain data?
Okay.
Thanks.
Hi, thanks for the talk. When you talk about that PR3 or PR4 prefers one model over the other, what do you use for that? And how about DESI and supernovae?
So you mean like the DIC or whatever?
Yeah, so do you employ Bayesian evidence and completely different scale?
So I haven't shown, we are going to use DIC, but I haven't shown because still, so for example, some of these ones we still, we want to find the complete minimum thing, we have the change. So I haven't shown it because maybe they may be not the last ones, but yeah, we will be using that. And if we can also some base factor.
Yeah, exactly.
Last question.
Hello, hi, good talk. I just wanted to ask if you could elaborate a little more on the difference between the PR4 data that you use and the one that have been used in the paper by the people that have released the helipop likelihood.
Do you mean the PR3 or?
PR4.
No, yeah, so the main difference, so if I were only showing AL or omega k, that would be, for just PR4, that would be what they did as the same data set. It's just that we added the non-CMB data, and also we checked the dark energy part. Okay. But yeah, we checked that for the ones they also ran, we got the similar results.
Okay, thanks.
Okay, let's thank Jacobo again.